Forgot to record 7. Okay, here we go. So what do we got? 10 point, what are we on? 10.3? Number 6? All right, so here we go. A space vehicle is traveling at 4,300 kilometers an hour relative to the Earth when the exhausted rocket motor, mass 4m, is disengaged and sent backward with a speed of 82 kilometers an hour relative to the command module, mass m. So if you watched the SpaceX thing, this is kind of the deal, right? We got two parts. The bigger part sort of drops off. Well, I guess it's the other way around this time, but one part drops the other part off. So anyway, here we go. Here's our rocket. All right, so in a minute, this thing is going to explode into two chunks, one of them with a mass 4m and the other one with a mass m. Therefore, this has a mass of 5m, right? Okay, and what it tells us is that this thing is moving along at a velocity of 4,300 kilometers per hour, and that's the velocity relative to the Earth. Okay, so that's kind of like our stationary observer, right, in the last problem. Everybody good? All right. Then it explodes into two chunks. So the back chunk is the fuel tank. That's got a mass of 4m. And then there's this little part up front where the astronauts live. Hello. That's got a mass of m. Okay. So you got to check the wording on this. It says the exhausted rocket is disengaged and sent backwards with a speed of 82 kilometers an hour relative to the command module. So, command module, exhausted tank. Okay? So this part is moving backwards, but not relative to the Earth. It's moving backwards relative to this thing. Okay? So I want to make sure you guys understand that doesn't necessarily mean it's moving backwards, right? The example I gave, a couple people asked about this one after school the other day. If you're in the second to last train of a car and you pull the pin out, releasing the back car, isn't it slow down relative to the train? Right? So you're going to like watch that train car descending into the distance? Am I making sense or no?
Yeah.
Right? Does that mean it's moving backwards? No, it's just moving slower than the rest of the train, and therefore relative to you it's moving backwards, right? Okay? So let's do this. Do you agree that this front chunk is going to speed up and the back chunk is going to slow down and maybe get pushed backwards, but I don't know? Okay, so let's do this. Let's call this VF for the front chunk. So we're going to call this VF. Now, when I say that, I guess I should be explicit. So that's the velocity of the front chunk. Let's make that relative to the Earth. Good? All right. So if I do that, I'm hoping you guys can figure this out intuitively without going back to the relative velocity equations that we learned last year, or last, I guess it was last year, but last card marking. What would this velocity be? If this thing is moving at a velocity of 82 meters a second or kilometers an hour backwards relative to this, then what's the velocity going to be? How am I going to write it? No, it can't do 4,218.
That's what I got.
I just took the new added velocity to 82, and I did a proportion. It's like I divided it by 5 and multiplied it by 4.
It's 4/5.
Gotcha. Okay.
It's momentum proportional depending on the masses. So
Yes, I gotcha. So that does work. So you're finding, I see. So you're finding the changes in velocity.
but I found what the change would be for the smaller one, and then I added that on to what was already there.
Okay, this
That
works.
concept,
This works. I don't know that it. I'm trying to show you guys how you can kind of consistently solve problems the same way, and I want this to look like total momentum before the explosion equals total momentum after the explosion, because that's how you should be approaching these conservation momentum problems. Okay, so what you're saying does work, and that's kind of a shortcut. And in doing that, you're processing a lot, but I don't know that everybody's sort of there. You know what I mean? So, all right. So, does it make sense that, okay, so this is moving forward at some velocity, right? This, relative to the front chunk, the back chunk is moving backwards at 82 meters a second. Isn't that the same as saying this is going forwards at 82 meters a second faster?
Yeah.
Right? So we can call this velocity VF minus 82 for the back chunk. Does that make sense?
Yeah.
Would anybody like me to write this in terms of relative velocity equations? Would that help anybody?
That would confuse me.
That's what I was worried about. That's why I didn't want to go that route. Okay, so are we good? All right, so now we just solve it. I say just like it's trivial, but so it's total momentum equals total momentum. So our total momentum before the explosion is mass times velocity equals total momentum after the explosion. Well, the total momentum after the collision is the momentum of this plus the momentum of this. So 4m times Vf minus 82 plus m times Vf. And so here's your equation that you got to solve. And just solve it for Vf. Follow, you guys? All right, and Johnny, to your point, you can kind of see where the 4/5 and 1/5 come in here, right?
Just find itself.
Okay. So Zach, I just overheard you say that makes a lot more sense. So where were you tangled up, or what did you try to do? I'm trying to figure out how to more effectively help you guys with stuff, because right now I feel like I'm just like, here's another problem. I feel like I'm not sort of helping you learn, and I'm frustrated with this, and I'm trying to figure out how to get better at it. So,
Well, okay, so looking back on it, I think the problem I had was I didn't realize how to define the total, like the scope of the momentum at the end, like what it applied to.
okay.
I didn't say it applied to everything. Like it almost, like for instance, I would have said that initial momentum just equals mvf or something like that.
Gotcha.
I just didn't realize that you treated it as its own system like that.
So better?
Yes, a lot better.
Everybody good? All right, cool. So that is number 6. So I think next on our list then is number 16.